Hello all, welcome back to my YouTube channel Anveshana Academy. This is Dr. Manjunath Chennapkot. Dear students, in the previous class we are discussing some numericals on conduction, heat transfer. With help of Fourier's conduction heat transfer equation, we tried to calculate the rate of heat transfer and thermal conductivity, and somehow we try to calculate the temperature gradient also. Dear students, come, we will move towards next numerical on conduction heat transfer. So first what I will do, dear students, I will read the problem, then I will solve this problem step by step. So numerical 5, that is the wall of an industrial furnace is constructed from 0.15 meter thick pyre clay brick having a thermal conductivity of 1.7 watt per meter Kelvin. Full stop. Measurements made during steady state operations reveal temperatures of 1400 Kelvin and 1150 Kelvin at the inner and outer surfaces respectively. Full stop. What is the rate of heat loss through a wall? That is 0.5 meter and 1.2 meter on a side. That means what, dear students, there is a pyre clay brick wall is there and it is having an area of 0.5 meter into 1.2 meter. One side it is exposed to the fire and another side is exposed to the ambient or atmosphere. Heat is going to transfer from inside to the outside. Then that wall having a thermal conductivity, that is 1.7 watt per meter Kelvin he has given, and thickness of that wall also he has given, that is 0.15. okay, so now for it's a very simple problem. So then what you have to do, we have to again step, what we have to do, we have to draw the schematic diagram for a particular problem. Okay, yes, dear students, you can see here now there is a pyre clay brick wall is there. Yes, it is a pyre clay brick wall is there. Okay, brick wall is there. Okay, fine. And it is having a thermal conductivity. It is having a thermal conductivity. I can mark here that thermal conductivity of the brick wall is, that is K, that is equal to 1.7 watt per meter Kelvin he has given. And there is steady state heat transfer, steady state temperature. Okay, and the temperatures he has given, one side I will take it as a inside. Okay, inside I will take it here 1 and outside I will take it here as a 2. Heat is going to transfer in this fashion. So inside temperature I will mark here as a T1, then outside temperature I will mark here as a T2. The heat is going to transfer from here to here. The heat is going to transfer in this fashion. That heat transfer I will mark here as a Q. Okay, so now the temperature he has given, then that wall, that brick wall having an area, that area is equal to how much he has given, 0.5 0.5 meter into 1.2 meter he has given. So that area also he has given. Then the thickness of that wall also he has given somewhere else, you can see around 0.15. that means what, we can take dx or L or T, whatever you want. Okay, these all things he has given. So now these things I need to draw it on a schematic diagram. How it is, that you can see here, dear students. 1 minute. Okay, fine. So now what is now? So I will take it, the front view I will draw here now. This is the front view. So this is a front view. What I will do, I will draw here now. So this is my front view. Heat is going to transfer from this end to this end. Okay. So now, 1 minute. Okay. Heat is going to transfer from this end to this end, or this space to this space, we can say. Then this is what high temperature region or inner surface we can call. The temperature at inner surface is 1400 Kelvin. That I will mark here as a T1. That means what, high temperature region, generally what I'm doing, I'm taking it as a T1. So then heat is going to transfer in this fashion. So that is what is T2. T2 also he has given, that is T2 1150 Kelvin, dear students. Okay, fine, that also he has given. Then that material, that brick wall having some thermal conductivity, that thermal conductivity represented by K, that K value is 1.7 watt per meter Kelvin, dear students. And area, you can see now, this is what, the plane, right? It is having a width of 1.2 meter and height of 0.5 meter. Through that area, the heat is going to transfer. That means what, you have to consider an area which is perpendicular to the direction of heat flow. That is what, Fourier's law we know already. So now quickly list out the given things now. Given what all things he has given. Just dear students, you can see now what is the thickness L, what is the industrial furnace, the thickness of that one brick wall is 0.15 meter. I will write it here. Fine. Next per brick, and it is having thermal conductivity. That thermal conductivity is equal to 1.7 watt per meter Kelvin. Okay, fine. Then measurement during temperatures. There are two temperatures. So one is T1. So I will write it here. T1 is equal to how much he has given? That is 1400 Kelvin he has given. I will write it here Kelvin itself. Then he has given T2 is equal to how much he has given? 1150 Kelvin he has given. Okay, at inner and outer surfaces respectively. What is the rate of heat transfer through an area? That area also he has given. Area is equal to how much, dear students? That is 0.1 minute. Okay, fine. So area is equal to how much he has given? 0.5 meter into 1.2. What will be the answer? See here, area is equal to how much? So 1.2 multiplied with what? 0.5. So how much? It is 0.6 meter square. 0.6 meter square. That is what? Area. So this is the thing he has given. Okay, fine. This is what area he has given. Fine. So now what I have to do? We need to, then he is asking to calculate the rate of heat loss or rate of heat transfer. That is total heat transfer is asking to calculate how much amount of heat is going to transfer through this wall. That we need to calculate. How to calculate that? To calculate that we are having an equation. What is that equation? Fourier's law of conduction equation. That I will write it here, dear students. So that is what? So Q is equal to minus Ka into dt by dx. So what is K? What is thermal conductivity? How much he has given? So some K is also given, right? K is equal to how much he has given? 1.7 watt per meter Kelvin he has given. He has given the data in terms of Kelvin. So I will write it here now. 1.7 into area is equal to how much you got? 0.6. Then highest temperature, that is 1400 Kelvin minus 1150 Kelvin divided by what is the dx? Dx or L you can take. How much it is? He has given. How much he has given? That is 0.15. So I will write it here. I will write it here 0.15, dear students, and do simplification. Do simplification. How much you are going to get? So 1.7 into 0.6 into 1400 minus 1150, okay, into bracket, okay, divided by what is the answer? So that is 0.15. Then how much you got? So Q is equal to what I can write? 1000, how much? 1700. Q is equal to 1700 watt. This is my final answer, dear students. So this is the total amount of heat transfer. That is Q is equal to 1700. Dear students, then how you got this final unit as a watt? How it is that we can see now. So we know Q is equal to already Ka into dt by dx. Substitute the units. Okay, what is unit for K? I will take it in terms of meter per Kelvin. So watt per meter Kelvin into area is what? Area, I will write it here. It is in meter square. Multiplied with what? Multiplied with what? Dt. Again it is in Kelvin. I will write it as it is Kelvin. The dx is in meter. So dear students, what will happen here now? So here meter, 1 meter, then one more meter is there, meter square get cancel. Then here it is Kelvin is there, here is Kelvin is there, get cancel. Then Q is equal to what is the final unit for heat transfer? That is watt. So therefore what we got it here now, dear students, the unit for heat transfer is, that is watt actually. So final answer is 1700 watt. This is how to solve the numerical. Thank you. We'll continue next class. Dear students, if you like the videos, please like and comment and share and subscribe. And if you want such informative videos, you can download my educational app, that is Anveshana Academy, from your mobile Play Store. Thank you.